Okay, so today we're going to learn about simple harmonic motion. So it's a kind of motion that's harmonic. By harmonic, I mean that it's going to oscillate. So if we plot the position versus time graph for a body undergoing simple harmonic motion, we should get something like this. And this looks like a sine curve. So if you plot the function x equals sine omega t, then you should get a graph like this. And this is the signature of simple harmonic motion. So that's what harmonic means. Okay. So the first example that we're going to look at for simple harmonic motion is the spring. So as you have seen before many times in your day-to-day lives, that if you stretch a spring and let it go, it oscillates or rather vibrates. So if you have a spring attached to a rigid support and a mass m attached to the other end of the spring, if you pull the mass to a distance x from its equilibrium position and let it go, then the mass will oscillate. And if we plot this position x as a function of time, we will get something like this. So this is simple harmonic. And there are certain parameters that characterize this curve and hence also the motion. One is the amplitude. So that's the maximum displacement that the mass can or the object can go from its equilibrium position. So we call that the amplitude. It is the height of the graph, the maximum height. And the other thing is the frequency, or rather the period, which are related. So the period is the time taken by the body to complete one oscillation. So one complete oscillation happens in a time that's called period. So that's the definition of period. We denote it by the capital letter T. It's in seconds, and obviously amplitude is in meters, because it's we're measuring position, which has the unit of length. So if we look at the spring, then the more we stretch it, the more the spring will pull back, right? So that we can imagine intuitively why that happens. So we also know that the force, to a good deal of approximation, should be proportional to the displacement. Now, both force and displacement are vector quantities, so the actual equations should have arrows on them. But since we're doing a 1D problem here, like before, the vector signs will not really matter, and it will just be, all the information about the direction will be contained in the sign. So the equation for force given a spring is the translation of this into mathematical terms, which is just F equals minus k times x. So this minus sign says that the force is in the opposite direction of the displacement. So if you pull the object here, the spring will pull it in the other direction, and vice versa. So that's the equation we need. This is also known as Hooke's law. And this holds up till a certain point. So if we keep on stretching the string, after a certain point the string will snap and then or get deformed, and then this will not hold. But in the regime that we will be working, this equation works fine. So this constant k is known as the spring constant, and it has units of Newton per meter. Or if we write everything in fundamental units, it is kg per second squared. Okay. So this spring constant, we can determine the spring constant by plotting the motion of the object like this, because the spring constant will be directly related to the period. So, and the formula relating the period to the spring constant is this. So the period, so you see that the period is inversely proportional to the square root of the spring constant, and hence the higher the spring constant, the smaller will be the period, which can also be understood intuitively, because a high spring constant means the force will be greater for the same amount of displacement, and for greater force, the object will be pulled faster, so it will take lesser time to complete one entire oscillation. So this formula makes sense intuitively, and this m here is the mass of the object. So the period is determined by two things, the mass and the spring constant. And the amplitude, well, that's just like an initial condition. It depends on how much you stretch the string. So it's not really the property of the mass spring system, but rather it's an initial condition that that we are going to choose for our experiment. And given these two, we can completely characterize the motion. So, and the other thing that is interesting about this is that the total energy of the mass spring system will consist of a potential energy and a kinetic energy, kind of similar to the ballistic pendulum that we did the other day. And as we know that energy is conserved, it can neither be created nor destroyed. So this is a constant. But however, potential energy and kinetic energy visually are not conserved, but their sum is a constant. And for a spring system, potential energy is given by this equation, which is half kx squared. And kinetic energy, as we discussed before, is just half mv squared. So this has to be a constant. And so let us denote that constant by E. So when the mass is farthest from its equilibrium position, the velocity is zero. That's at the point when we are releasing it, right? So then this part will be zero and this part will be maximum and will be equal to E. And as the object, after we release the object, it will slowly accelerate and gain velocity. So the kinetic energy part will increase, but this part will decrease because it will move closer and closer to the equilibrium position. But this increase and decrease of P and K will be such that their sum is always constant. If we plot with respect to time, then if this will be our potential energy and this will be our kinetic energy. So when we see that when the kinetic energy is maximum, the potential energy is zero, and vice versa, such that their sum is always equal to E. However, we won't be plotting this graph for this experiment, but it's good to know that this relation also holds for the simple pendulum, which we will discuss next. Okay, so the second part of the experiment will be a simple pendulum, and as we know that if we have a pendulum which is just a mass hanging from a string from a rigid support, and if we slightly move it from its equilibrium position by say a distance x, then gravity will pull it back and it will oscillate like this. So again we see that we have an oscillatory kind of motion where the position first increases, reaches a maximum, then decreases, reaches a minimum, which is negative, and then again goes back to zero. So it will also be a simple harmonic motion, and the period for the pendulum is given by root over 2 pi root over of L by G. Yeah. So this for a pendulum, the same things that apply for a spring, the same concepts I mean, will also hold for the pendulum. The total energy will be a constant. So the potential energy will now be a gravitational potential energy, because gravity is the restoring force here, which was the spring, in the previous case, but in this case it's gravity, and the kinetic energy will be the same, and it will also be constant. And if we plot, the plot will also be similar to the previous case, two parabolas. The non-intuitive part is that here it is just proportional to the height, so and not h squared. So it's kind of non-intuitive that despite having a linear dependence, our potential energy is still a parabola. Well, it becomes clear if we write h in terms of the displacement theta. So h is just the height from the equilibrium position, and the height will be the length of the pendulum times cosine theta. sorry, 1 minus cosine theta. And for small angles, if the displacement is very, very small, this can be approximated as length times theta squared. So if we substitute that, in here we have mgl times theta squared plus half mg squared. I'm sorry, it should be half here and a half here. So again, we see that there are two parabolas and the sum of them will be a constant. So when the angle is maximum, the velocity will be 0, and when the velocity is maximum, the angle will be 0. So this is completely identical to the pendulum, except that the variables are now different. Instead of distance, we are measuring angle, and the restoring force is gravity and not the spring. But other than that, the motion will still look like a sinusoid. So these kind of graphs are called sinusoids because they resemble a sine function. And the period, as I wrote before, is 2 pi times root over L by G. The key point to note is that for this, in both cases we have a mass m that is oscillating. So for the spring, the mass was attached to the spring, and for the pendulum, the mass is just hanging from a support. But how the mass affects the period is different for the spring and the pendulum. So for the spring, we see that the period is directly proportional to the square root of the mass. So if we increase the mass, the period will increase. But for the pendulum, the period has no mass dependence. So no matter how heavy this is, the period will still be the same. But the period does depend on length for the pendulum, which it doesn't for the spring. So irrespective of how long or how short our spring is, the period of the spring will remain unchanged. But for the pendulum, that's not the case. So these are the two key points that we need to remember for this experiment. So this is for the pendulum. And in the experiment, we will do both of these for different masses and different lengths and verify this hypothesis that the period does depend on the mass for the spring and doesn't for the pendulum, and vice versa for the length. Okay, so now we're going to do the measurements. So as usual, there will be a capsule file, and it will be attached to a sensor that will record all the data. So first we will do the spring part, and the first measurement that we need to do is we need to choose two masses and then measure the period for each of those. And after choosing the masses, we can move forward to measuring the period.
So we have 50 grams on a 50 gram hanger. Pull it down just out of equilibrium and let it oscillate.
Yeah, so as it oscillates, the sensor records the data, and we should get a graph like this. So as you can see, it's a sinusoid, and then we can measure the period using the cross using the smart tool like we did before. So this is the crosshair. Then we should click on add coordinates or delta tool. Then we can select the two peaks. One of them is here. So you can find the horizontal distance between two peaks, and since the horizontal axis is time, that should give us the period. And then after measuring the period, we repeat the experiment with the heavier mass and then do the same thing. So we should be doing now.
Now we have 100 grams on the 50 gram hanger. Pull it just out of equilibrium.
Yeah, so as you can see, there is a different. We have another graph for part 2 for the different mass, and clearly the period is different, which is what we expect. But then we have calculated the mass. We have measured the mass, so we can calculate. We can calculate the period, and that gives us a theoretical value. and then we can measure the period here, which will give us a measurement. So we have two different masses and two different plots. So the green one was for the 100 grams mass, and then the orange one is for the 150 grams mass. And so clearly the periods are different. So then we can use the smart tool like I showed before to measure the two periods and then compare it with our theoretical periods and find the percentage error using this formula, which says that the percentage error is just the difference between the measured and the theoretical value over the theoretical value times 100. And don't forget to take the absolute value, because error can never be negative, it's always positive. And the other part of this experiment is to measure the spring constant, where we use that. So if we hang a mass and do not pull it from its equilibrium position, it will stretch a bit from compared to the point when there was no mass. So this difference in length is our displacement. So as you can see,
with no mass.
So with no mass, we have a length with the natural length of the spring, and then when we put a mass, the length increases. So the first initial length will be our L naught, and the new length will be L. The difference will be our displacement from the equilibrium position. And if we plug in that to our formula of force equals kx equals mg, then from that we can find k, because m is known, g is known, and the length difference we have measured. So then we can find the spring constant and use our also calculate the uncertainty of the spring constant by taking into account the instrumental uncertainties of the measurement of length and mass, and propagate them using the rules of propagation of error. So that's the spring part.
Okay, so we have our first pendulum mass of 20 grams. We're going to pull it back about 10 centimeters and let it go before we run the sensor. We run the sensor now to collect our data. Okay, now we have 50 grams on our pendulum, same length. We pull it back, let it run a little bit before we start the sensor. We can start it now. Okay, now we're at 100 grams, same length. We're going to pull it back a little bit and let it run. And then start the sensor now. And you should be able to determine period from all of these. Okay, so I've shortened the length of the pendulum, and I've put the first mass of 20 grams back on. We're going to measure the period now. Pull it back, let it settle, and record. Okay.
So the recorded data will look something like this. And again, like as in the case of the spring, we will use the crosshair, the tool that looks like a crosshair, to find the periods, which is just the difference between the x-axis values for two peaks. We will do it for all the 3 runs, all the 4 runs, and then analyze the data and answer the following questions. The last question is a bit tricky, so we were planning to give you hints on how to do that. So it says that this experiment is being conducted on a different planet, and the length of the pendulum is given, and the period is given in the statement that 100 vibrations are completed in 320 seconds. So from that we have to find the period, and then we know the period, we know the length, we have to find the g on that planet. And because it's a different planet, g is not 9.8 meters per second square. So we'll do that now in this way. Okay, so as usual, we're going to use this formula of period for the pendulum. But in this case, we are not finding the period from the length. We're doing the reverse thing. So we have to work out a bit with this formula. So if we square both sides, we get that t squared equals 4 pi squared L over g. And if we take g this side and bring t squared down, we get g equals 4 pi squared L over t squared. So then t is just, so it's given that the Pendulum completes 100 oscillations in 320 seconds. So T is just 320 by 100. That's just 3.2 seconds. So we plug that here. The length is given as 1.6 meters. So we plug that here and calculate G for that planet. And this G will probably be different, will not be equal to 9.8 because it's a different planet. So you have to plug in these numbers and find the actual value of G.